In our previous class, we started with modern physics. Now this graph we have discussed in our previous class, which is plotted against photocurrent and the anode potential. We saw that if I3 was greater than I2 and it was greater than I1, we have seen the following type of distribution curve, which shows that here this I1 is now at the lowest point on the graph, then the I2 is on the higher point, and then is the I3. We have also seen that when we are decreasing the intensity of the light, the photocurrent will not stop because from the origin it is at somewhat point. So for that we have to further on decrease the intensity and make this intensity in the negative, which we are calling as retarding potential, at which the photocurrent will completely stop. And we can also say that this part which we are observing over here, this corresponds to the anode potential, that is the nu zero or the stopping potential. So this is stopping potential. When we see the frequencies of the incident light along with the anode potential, we see that if we vary the frequencies in the three different phases where this frequency is highest among the all, we see that as we are increasing the frequency of the incident light, the kinetic energy of the emitted photoelectrons will also increase, and those photoelectrons which have the highest kinetic energy will require more negative work function or will require more negative stopping potential in order to stop this photocurrent or make this photocurrent to the zero axis. Now if we take two different metals and we plot the graph for metal A and metal B, and the coordinates are stopping potential and the frequency of incident radiations, we find out that the linear curve is being shown over here, and this dotted line represents the negative potential. So now what conclusions can we draw from the given graph? Conclusion number 1. Stopping potential and frequency are linear. This we have already seen from this graph, where we saw that the stopping potential, which is this one, and the frequency are on the linear scale, and this part which is still left over here, this part corresponds to the stopping potential, means this much at least we have to give so that we can increase the frequency and we can increase the photocurrent amount. Now let's see the next one. The minimum frequency required of incident radiation below which the photoelectric current does not occur is called the threshold frequency. It is the minimum frequency which is required for the photoelectric current to take place. The next point says that the kinetic energy which will be emitted of the photoelectrons is directly proportional with the frequency. As we increase the frequency, the kinetic energy will also increase, but it will be independent of the intensity of the light which we are providing. Point 4 says that we require at least a threshold frequency after which we can observe the photoelectric effect because the minimum frequency that will be required for photoelectric current is threshold frequency, and below that we cannot observe the photoelectric effect. Students, we already know one equation, which is energy is equals to Planck's constant multiplied by the frequency. So this here we see a direct relationship, that is energy will be directly proportional to frequency. So the frequency of some lights will directly affect the energy and the photoelectric effect also. For example, in the first case, when I take blue light, so the blue light has greater frequency and it has less wavelength. So we can say that if the frequency is greater, then the energy will also be greater and the photoelectric effect will be enhanced. So here when we see the effect of photoelectric effect is more. In the second case, when we take the red light has frequency less but the wavelength is more. But since frequency is less, the energy will also be less. And that's why photoelectric effect is observed less. But we already know that what is the meaning of threshold frequency. The threshold frequency is that minimum frequency which is required by any of the electron to get emitted. Means for the emission, we require at least this much of threshold frequency, which is represented as nu naught. Means here when we see that any of the photoelectron will not be emitted till it does not get threshold frequency. So when we talk about over here, we see that this energy, this frequency should be either greater than or equal to threshold frequency. So when we write the modified form of the equation, we get E equal to h nu naught, where this nu naught is the threshold frequency. Means if we are getting this much threshold frequency, then we are able to emit the we are able to emit the electron. So we can say that the photon, which comprises of the intensity radiations, is equal to the electron. So this is the important thing that you have to learn, and this is our equation which we have to learn. So now when we see some of the important graphs, let us see the combined effect of all the phenomenon that is taking place and their graph. First we see the graph of frequency and the stopping potential. This frequency is threshold frequency only. So when we see the graph does not start at origin, it comes to the bottom, and here we can say that this is the angle theta that the slope makes with this y-axis. This y-axis denotes the frequency, and this is the stopping potential. Means we say over here that the minimum amount of threshold frequency we require so that the photoelectric current will take place, we have seen over here. And when we plot here, the value of this point comes out to be minus of work function divided by the charge, or that is the electron. And here if we find out the slope, we found that tan theta equal to h upon E, and this gives us the value of the slope. Let's see the second graph. The second graph shows the frequency and the photoelectric current. When we plot the graph of frequency versus photoelectric current, we find out that the graph comes out to be like this. So here we can say that the photoelectric current and the frequency both are independent of each other. This we can observe from this graph easily. So here we can say that there will be no effect of frequency increasing, at least if we are providing threshold frequency. We are observing the photoelectric current is taking place, it will be starting, but after that as we are increasing the frequency, there is no effect of photoelectric current. Means frequency and photoelectric current are not related to each other or are independent of each other. When we see the third graph, we are now plotting the graph of intensity versus stopping potential. We get this type of graph. If we put here stopping potential and here intensity, we find this type of graph, which again shows that the intensity and the stopping potential are independent of each other. Means for a fixed value of a stopping potential, the intensity will remain constant. As we are increasing the intensity, the value of stopping potential will not get affected. But when we talk about the frequency and the stopping potential, there we observed a different type of graph which we already discussed, and it was just like this. If this was one coordinate, we saw three different frequencies. So this was for frequency and the stopping potential, but this frequency and the intensity have two different values. We already discussed that incident is directly proportional to frequency. So you might think that if this frequency and stopping potential have some graph, then definitely the intensity and stopping potential should also have the same type of graph. But this is not possible. Here we can see that the intensity is independent of the stopping potential, or for a fixed value of stopping potential, there is no effect of intensity on that stopping potential. When we take the last type of graph, we see this is between the photoelectric current and the time lag. We find out that when we plot the graph, for a certain value, the photoelectric current goes on like this way, and then afterwards it becomes constant. So from here to here we can have this much average time as 10 to the power minus 9 seconds. This is the value. Means photoelectric current is a very quick procedure. It takes place within 10 to the power minus 9 seconds. There was one wave nature of light which proved everything that we studied till now wrong, and after that came the Planck's quantum theory. Now he said that instead, when we talk about the radiations as a form of wave, we can assume them as a form of quantums, and these quanta are actually what we call as photons. Now these photons which comprises the radiations have some momentum, and the momentum of these photons will be momentum, which we can represent as P, will be h nu by C. And this nu can be written as 1 upon lambda, so we can write as h upon c lambda. So the formula of momentum can be written as h nu by c, which can further be written as h upon lambda c. And when we talk about further, we can see that this c will actually get eliminated from over here, because we know that momentum, that is p equal to h nu by c. But here this nu by c, we already know that c upon nu equal to h. So here this is nu upon c, which can be written as 1 upon h. So we are writing as h upon this is equal to lambda, and this is also equal to lambda, so we can write as h upon lambda. Momentum formula is h nu by c, which can be written as h upon lambda. Now this h is nothing but Planck's constant, and the value of Planck's constant is 6.67 into 10 to the power minus 34. And what is the unit of Planck's constant? So unit of Planck's constant is joule second, and the dimension of the Planck's constant is m1 L2 T minus 1. So this is the Planck's quantum theory.